Sure, it's over here.
Okay. Okay.
We good? Okay. Sounds good. Okay. Welcome to the first afternoon session of today's ZKProof workshop. So the next session is going to be three loosely connected talks about analysis and assumptions of different proof systems. And the first talk will be given by Gaspard Anthoine. What a wonderful world zkSNARKs in the algebraic group model are universally composable. Gaspard, take it away. Thanks.
Thank you very much for the introduction, Matteo. So yes, thanks to be there. Today I will present you my very recent work with my colleague at EMDR, Dario Fiore and Mark Pancholi. And we will talk about the universal composability of SNARK, and in particular SNARK that straight line simulation extractable. So first, a bit of motivation about why do we care about universal composability of SNARK. There is some pragmatic reason. The first one is usually SNARK are used in composition. They are used as a building block in more complex protocol. And this is a notion that standalone security fails to capture. And this goes straight to the second reason. When you prove that a SNARK is universally composable, then it is easy to build new protocol using it. And this gives a very nice interface for designers. And there is even a more pragmatic reason. That's that if you have straight line simulation extractability for SNARKs, then you are already very close to getting UC security. There is this paper from Grove in 2006 that showed that non-malleability and straight line black box extraction give you UC security for ZKProof. So how do we model UC security for SNARKs and NISIX? As always in UC, we want to have a real world and an ideal world. And we will play against an environment that in the real world has access to a prover verifier and whatever else he wants. And all the parties has access to a CRS. And in the ideal world, we have the environment that plays the game against a UC simulator that needs to convince him that he's not able to distinguish between the real world and the ideal world. Okay? And in our case, we will focus on local CRS modeling of NISIC, which means that the UC simulator generates some different CRS for each parties in his head. Okay. So on top of this, because we need some idealized model to get straight line extraction from SNARK, straight line extraction means that you don't have to rewind to extract from the proof. And this is only possible if you have some ideal model for SNARKs. So in a very recent TC paper, Bobbles and al. proposed a global observable generic group functionality. And the goal of this functionality is to give access to a group oracle as a shared resource. But this poses one problem. That is that because the resource is shared, it's not the UC simulator that does everything in his head anymore. And you have to give some observability rules such that the UC simulator can still extract proofs. But you need this observability rule to not give too much observation, because otherwise you would break the zero knowledge of your zkSNARK. And they managed to do this by giving this very nice observability rule that is when you do an operation, if it involves a group element from different session, then you add it to an observation list that everyone can query. Otherwise, you just do the thing as a normal oracle. Okay, and yes, this is a simplified version of the functionality. In the TCC paper, the functionality is more complex. For example, if you have a new element that is appearing that is not assigned to any session yet, you can add it to an arbitrary session that you choose. They also define a symbolic functionality that creates a perfect separation between sessions. I will not come too much into the details about this because this is not important for the talk. What's important is how does it look like now. As you can see, as before, prover verifier adversary environment, everyone has access to the CRS. And on top of this, they have access to this global OGGM. And the simulator, in the ideal world, the simulator also has access to this global OGGM. Okay. And here you can see why he actually needs to be able to observe, because otherwise he would not know what the environment is doing with this functionality. So there is one big problem with this. That is, you need to be able to find actually the representation of an element. What I mean by representation is that because the observability doesn't give you access to every group operation, it only gives you access to operations that mix elements from different sessions. You don't see, for example, an honest proof algorithm in session SID prime. And the UC simulator needs to be able to come up with a representation with respect to a specific basis. So they describe this find representation algorithm that basically gives you a representation of a group element for one basis. Very simple example. Here we have H that is with respect to two different group elements. Let's say you are just interested in getting the representation in basis GA. What you will get at the end of the algorithm will be 3. Okay, and then this is the main technical point of the wallpaper, is that from this, you need to be able to reprove that what you get after getting this representation is enough for you to extract. So you need to redo the simulation extractability proof such that it matches what you get from this find representation algorithm. Okay. So to put a bit more of context, now that I explained what is this global GGM functionality, let's just look a bit about what we know about SNARKs and UC modeling. So we know that from rewinding it does not work. Then we have some specific compiler from CRS or a random oracle model. I will not enter too much into the detail, but you need to quite change the protocol if you want to have UC security in these models. And then in the AGM, we have a specific UC AGM, but it doesn't work for NISIC. And the main reason is that in the AGM, only the adversary has to explain what he's doing. And for example, if you have like a non-necessarily generated proof, then you don't have the explanation that comes with it. And therefore, the environment can start feeding proof from different sessions. And in the OGGM, as I told you, we have only a proof for growth 16 because you have to redo the whole analysis. So the first question we can ask is, okay, can we have a very generic reduction from simulation extractability to UC? Okay, can we take any SNARK that we know that is simulation extractable in Shub GGM and infer UC security from it? And then another question is like, most of the simulation extractability proof we know for SNARK are done in the AGM. So can we reuse also generically this proof in the AGM? And at the end of this talk, I hope you will be convinced that yes, we can answer yes to these two questions. So let's go for a first part of a recipe to get a very generic reduction. So let's say that, this is a slight modification of the simulation extractability game, but this actually matches exactly what usual simulation extractability game do in the real life. So basically the idea is that you can split the extractor in two parts. The first part, that is really the core of your extractor, that identify the important group element you need with respect to a given basis, for example, your CRS. And then you give it to FindRep. FindRep will extract the representation with respect to a basis. And you can then run a kind of dummy extractor that will just reconstruct the witness from the representation. And this is mostly syntactic. And this is actually syntactic because we want to match what you would get in a standalone security game. So what you might wonder is, okay, even doing this, it really looks like before. No, you just run FindRep. How can you avoid having to reprove things from the start? And to answer this question, we have to go and take a different angle. We have to look at the environment and think, okay, can we go for the straightforward, the dream way? Can we reduce the UC adversary to a standalone adversary? And now I will try to convince you that because simulation extractability in the standalone setting is already very close to UC security, it's enough. So let's just define a bit what is a standalone adversary. It's the adversary that most of you must be used to. It's like just you define your security game with a challenger, and the adversary talk with the challenger. He also has access to the GGM, and at the end, he must be able to come up with a proof for a false statement. Okay, and we are taking here, like for the sake of generality, we will talk about index relation, but this is not important for the talk. And here I'm also showing you a very simple UC wrapper that allows you to have a very similar game in the UC world and in the standalone world. And again, the idea at the end is that we want to reduce our UC environment to this standalone adversary. In other words, we want this standalone adversary to run the UC environment as a wrapper. I mean, the standalone adversary wrapping the UC environment. And having a forgery coming from the UC environment give you a forgery for the standalone game. If the standalone game is hard, this should not be possible. Okay, so let's go back and look at what it looks like now. So what we have is an environment in the real world that has access to prover, verify, or whatever it wants, the GGM functionality and the CRS. And we want to transform it to an environment that only talks with a standalone adversary. He can do proof, verify anything he wants. The adversary will forward proof and verify for the session SID to the challenger, and otherwise he will simulate everything else. And also, important thing, here you can see that it's not the GGM, but it's the normal SHUP GGM without observability that you have access to. And actually, this gives a bit of a problem because the adversary still have only a partial view, and in particular, the environment should be able to ask for observability query, to ask to find the query that would mix elements from different session ID. And the standalone adversary doesn't see the query that are made by the challenger to the group oracle. Okay? And you might wonder, okay, why is it a problem? The challenger is trusted. What can happen? So I will show you a simple example. Let's say that A and B are in the CRS of our proof system. And let's imagine this interaction between the environment and the adversary. Okay, so the environment asks to create a proof for SID. The adversary asks the challenger to create the proof. The challenger computes some things and output the proof. Here, the element H is not the proof itself. It's just some internal computation of your challenger. And then you forward the proof to the environment. Now, for some reason, the environment comes up with H. And the thing is, like, B, the standalone adversary, never saw H. So it's the first time he sees it, and the environment says, OK, give SID prime to this element. So the adversary says, OK, I'm giving SID prime. And then the interaction continues. The environment has to do an operation with this H and A. And here you can see that there is a problem. The problem is the view is different from what the standalone adversary is able to infer and what the UC view would have been in the simulated world. And this is a problem because now when you ask to do this computation for H prime, adversary B will add it to the observation list because it would mix two different SID. And trivially, by calling the observation, the environment can distinguish. So yeah, you can see that there is some subtlety about doing this reduction. So the problem is, okay, the adversary can forward, prove, and verify queries, but he cannot see what is happening inside. What he only sees is the final proof. And because of this, we need to argue that the full representation isn't needed. Okay? What you only need is to be able to decide if there is some foreign component or not at the end of a computation. And actually, as long as what I just showed you don't happen, you are always able to do it by using the group oracle to test if things cancel. Okay, basically because you track every query that the environment is doing, you are able to reconstruct part of the query that is in SID prime and check if this part can sell. And this is enough as long as the environment doesn't guess some internal group element of the prover. And we argue in the paper, it's a bit technical, but we argue that it shouldn't be able to find some internal group element. And therefore, because the only thing you need to do is to classify and not to reconstruct exactly the group and how it was built, it's enough to get the partial view. Okay. So are we done yet? Nearly, but not yet. So what we have right now is UC for any any simulation SNARK that is simulation extractable in the GGM, but we don't have UC for any SNARK that is simulation extractable in the AGM, for example. And even on top of this, we would need to add a random oracle if we want to capture Fiat Shamir. But this I will not extend too much on it because this is kind of easy to do, as long as we need a non-programmable random oracle. So now let's see how we can go from the AGM to SHUP GGM in a meaningful way, keeping kind of a black box way. Okay, so what do we know about AGM and GGM? We know that you can go from AGM to type safe or more GGM as long as you have an adversary that is type safe. Type safe means that you access the group representation only as a black box. Okay, this is a result from Jaeger and Moine 24. And we know from Zandri paper, to label or not to label in 22, that if you have a single stage adversary, then you can go from more to SHUP. Okay? And single stage just means an adversary that shares state across all the game. It can have different interface, but it must share the same state. Good. So now we have a very clear path. What we want to do is get our simulation extractability proof in the AGM, check if it is type safe, and then when it's type safe, check if it is single stage, and then we have a simulation extractability in the GGM. As I said, then it's also possible to have a type safe random oracle, because maybe you wonder, like, what does it mean to have type safe, to have a random oracle in a type safe model in more GGM? Actually, it's from the latest paper of Jaeger and Moine again. They defined the type safe random oracle. In the paper, we define it in a bit of a different flavor, but I mean, things follows the same way. And then we also show that you can go from this type safe plus type safe GGM to normal SHUP GGM plus normal random oracle. And from this, we can actually concretely look at simulation extractability proof for Plonk and Marlin and see what is happening. So yeah, the idea is to type this paper from Faonio, Fiore, and Russo 24 that prove simulation extractability for Plonk and Marlin. For information theoretic reduction, it's kind of trivial because you just parse bit string and you forward polynomials. For computational reduction, it's a bit more work, but it's also quite simple because the main thing you need to ensure is that a few theorems are type safe and that the underlying assumptions are generically hard, but this is already done in the paper. So basically, you have a generically hard underlying problem. Everything is type safe. Everything is single stage. So not much work to do about this. And this comes to the conclusion that directly what we managed to do is like first look at the GGM and prove that from a standalone adversary in the GGM, I mean, you can reduce this standalone security to the UC security because you have a straight line simulation extractability in a black box way. And then we prove that you can take any straight line simulation extractable proof from the AGM, type it, and then lift it to the GGM. And therefore, this directly yields that Plonk and Marlin are UC secure. You don't have to change anything in the protocol. There is no overhead, and it's following some very classical UC secure functionality. In particular, you don't need a programmable random oracle. So surprisingly, at the end, this comes up to be quite direct. Still a bit of open question, because I heard this morning that I needed to add a slide about open questions. So I think one of the main and hardest questions is, can you share the same CRS? I think, yeah, this is hard because there are some impossibility results around this, that you can't have UC security with non-local resources. So yeah, this is a hard question, and this is the main limitation that in our case, we assume that the CRS is different for every SNARKs. Then the question is about the transparent SNARK. This becomes also quite more complex, because you need to add a programmable random oracle on top of the AGM if you want to do straight line simulation extraction. So yeah, this is also a nice question. And then adaptive soundness, that I think should be more about looking at it and solving it. That's it. I hope I have been clear. I'm a bit in advance, so.
The speaker? Yeah, we have time for several questions, actually.
Can you maybe clarify a bit what do you mean by adaptive soundness in these open questions?
Okay. Yeah, I mean, in our case, we assume. So it's about. Wait, let me go back. Okay. So in this case, we assume that the environment, I mean, just gives. I mean, he can play however he wants with the proof, but at some point, he just gives you the false proof, and it's fixed. Adaptive soundness would be being able to. Actually, that's a good question. Now I'm wondering exactly what I meant. Maybe Mag, that is there, could answer this, because.
I mean, we only consider static corruption, where the environment needs to corrupt somebody before it starts the experiments. But in adaptive, I guess you wouldn't require the simulator to also explain how it came up with the proofs, because it can then corrupt parties adaptively. It's just a stronger model. You need adaptively secure simulation extractability maybe for that.
Any more questions?
Thanks a lot.
I have a question then. So you write at some point black box simulation extractability in the GGM. Does BB comes for free actually, or?
Yeah, BB comes for free. I mean, when you look at the no, actually it was this slide. I mean, as long as you can run, I mean, you replace your prove and verify algorithm by a simulator and extractor. And it's just a black box. You don't need to see anything internal. Mm-hmm. It just, I mean, again, because you don't care about actually what is happening, what the challenger is doing. So you don't need to see what is happening. The only thing you need is that it's a trusted algorithm.
Okay. I have one more question then, unless there are questions from the audience. No. When you mentioned here's one more question. When you mentioned shared CRS, here's a dumb proposition. I wonder if it works. So is it possible, suppose you have a Plonk-like setup, updatable and such, use that for one session, you want to use it for different proof systems, say Marlin and such. Now, you cannot share the CRS. Your model, you need to have a new CRS, right? So it cannot be shared. Can I run an updating protocol with a few parties for a little bit, and that's my new CRS? Does that count?
So you mean you start from a shared CRS and then you update it? I guess this works. I mean, I think maybe. I mean, I think it works because the idea of having this, different CRS is just that you need to be able to distinguish between a group element from different session. And the problem is if you have the same CRS, then things will start to algebraically mix and you will not be able to separate session. I think if you do this and you don't generate proof before having run your update setup, then yes, it's like a different CRS.
Okay, just sanity check.
Yes.
Sounds good. Let's send the speaker again.
Thanks.
"25 minutes plus 5 minutes for questions."